Hello everyone. In this session, let us understand task-based application models. So there are many applications which are based on the task model. So these applications can be differentiated based on the relationship that they have with respect to the task and presence of dependencies or some other conditions. So let us see what are the different applications that we can have under this task model. So first one is parameter sweep application. So parameter sweep applications are specific class of embracingly parallel applications, which we are going to discuss in the next slide. Embracingly parallel application for which the tasks are identical in their nature and differ only by specific parameter used to execute them. Parameter sweep applications are generally identified by a template task and a set of parameters. The templated task defines the operations that to be performed on the node for the execution of tasks. The template task is a parametric and parameter set identifies the combination of variables whose assignments specialize the template task into specific instance. The combination of parameters along with the range of admissible values identifies the multi-dimensional domain of the application, and each point in this domain identifies a task. Any distributed computing framework providing support for embracingly parallel application can also support the execution of this application, that is parameter sweep application, since the tasks composing the application can be executed independently from each other. The only difference is that the tasks that will be executed are generated by iterating over all possible and admissible combination of parameters. This operation can be performed framework natively or tools that are part of distributed computing middleware. For example, Nimrod G is natively designed to support the execution of parameter sweep application. Next we have embracingly parallel applications. Embracingly parallel applications we already discussed in the previous section. They are the most simple and intuitive category of distributed applications. Embracingly parallel applications are constituted by a collection of tasks that are independent from each other and can be executed in any order uh, that might be of the same type or of different type, and they do not need to communicate among themselves. This category of application is supported by the majority of the frameworks for distributed computing. Since tasks do not need to communicate, there is a lot of freedom for the way in which they are scheduled. Tasks can be executed in any order, and there is no specific requirement for tasks to be executed at the same time. Therefore, scheduling of these applications is simplified and mostly concerned with mapping of tasks to available resources. The frameworks and the tools supporting embracingly parallel applications are your Globus toolkit and Boeing and Aneka. Next we have MPI applications. These are the applications again under task-based model. MPI stands for Message Passing Interface. It is an application for developing parallel programs which communicate by exchanging messages. Compared to earlier models, MPI introduces the constraint of communication, which involves that MPI tasks need to run at the same time. MPI has originated as the attempt to create a common ground from the several distributed shared memory and message passing infrastructure available for distributed computing. Nowadays, this becomes a standard for developing portable and efficient message passing HPC applications. Interface specification have been defined and implemented for C, C++, and Fortran. MPI actually provides a developer with a lot of facilities like manage the distributed environment where MPI programs are executed. It provides facilities for point-to-point communication. Even it provides facilities for group communication, and it supports for data structure definition and memory allocation, and it supports for synchronization with blocking calls. Okay, so why we are using these MPIs? So the standardization, MPI is the only message passing library that can be considered as a standard. It is supported on virtually all HPC platforms. Practically, it has replaced all previous message passing libraries. Then portability. Portability is one of the features of this MPI. There is a little or no need to modify your source code when you port your application to different platforms that supports the MPI standards. Then performance opportunities. Vendor implementations should be able to exploit native hardware features to optimize performance. Any implementation is free to develop optimized algorithms. So that means you can enhance the performance of the hardware under this MPI applications. And then functionality, there are over 430 routines defined in MPI 3, which includes majority of those in MPI 2 and MPI 1. So MPI uses object called communicators and group to define which collection of processes may communicate with each other. So you can see here in this shaded oval, there are so many processes with unique ID identifier or IDs, okay, with which these processes can communicate with each other. Most MPI routines require you to specify communicator as arguments. Okay, communicators and groups will be covered in more detailed later. For now, simply use MPI, that is communication word, MPI underscore com word, whenever the communicator is required. It is predefined communicator that includes all of your MPI process. Within a communicator, every process has its own unique integer identifier assigned by the system. When the process initializes, a rank is something also called as task ID. This task ID is generated, which begins at 0. It is used by the programmer to specify the source and destination of messages. Usually, it is conditioned by the application to control program execution. That is a rank 0, then you have to do this. If rank 1, you do that, like that. Okay, so the format of this MPI program will be something like this. We will be having the header section over here, and this is a header section. Okay, and then we have a code section in between. Next to that, we have code section. Okay, code section, and in the third we have exit or termination section. Okay, termination section. So So this is the structure of the MPI uh, application program, where header section includes MPI include files and some prototype declaration, whereas in the code section, MPI, it is the initialization, that is environment for initialization or some coding to do work and message passing. Then finally we have something called as a MPI environmental shutdown, where the complete application can terminate. Okay, this is the standard format of MPI application programs. Next application is of type workflow applications. Workflow applications, usually scientific workflows, allows user to easily express multi-step computational tasks. Now, before that, we have to understand what is this workflow. Actually, the term workflow has long tradition among the business community, where this term is used to describe a composition of services that all together accomplish a business process. According to the definitions from workflow management, this workflow is actually defined as the automation of business process in whole or part, during which documents, information, or tasks are passed from one participant to another for action, according to the set of procedural rules. This is the standard definition of workflow. The concept of this workflow as structured execution of tasks which have dependencies on each other, uh, and useful to express many scientific experiments. So these are the few applications which are used in scientific experiments as scientific workflows, okay, that allows user to express multi-step computational task. Structured execution of tasks which have dependencies on each other, and scientific workflow is expressed by direct acrylic graph, that is TAG, defining dependencies among tasks. So here we have this diagram, which you can call it as a directed acrylic graph, which defines the dependencies among the tasks or operations. The nodes on this DAG represents the tasks to be executed in a workflow applications, while the connecting nodes identify the dependencies among the tasks and data path that connects the tasks. Okay, so in this figure we have uh, the tasks that are designed by circles or ellipse, while the files created by the tasks are indicated by rectangles. So here we have is a task, and curl is also tasks, which is going to give you a file like listing.txt, and like this here we have pegasus.html, and then again we have a task called as wc. Okay, so wc, which in turn gives you a count.txt file. So these are the few that is directed acrylic graph for the information. Then we have something called as a split workflow. Actually, split workflow downloads the Pegasus home page using the curl command, then uses a split command to divide into 4 pieces. The result is passed to WC command to count the number of lines in each piece. You can see here in this entire DAG diagram. So where this HTML file is downloaded, and gives you the split task, where it will generate part.a, part.b, part.c, and part.d as the files, and which in turn gives you the tasks like WC. Okay, and finally uh, wc command will give you the files like counter.text.a, counter.text.b, counter.text.c, and count.text.b. Okay, so these are the few examples to understand this split workflow. Here we have this is again a DAG, that is a directed acrylic graph, which describes a simple montage workflow. Actually, a montage is a toolkit for assembling images into mosaics. It has been specially designed to support the astronomers in composing the images taken from different telescopes or different point of views. Okay, the toolkit provides several applications for manipulating images and composing them together. Some of the applications perform background reprojection, perspective transformation, and brightness and even color correction can be done. This workflow describes the general process for composing a mosaic label. The label put on this, here you can see the label on the right describes the different tasks that have to be performed in order to compose a mosaic. Okay, here you can see the transfer the template header or transfer the image file, and next reprojection of the image, then calculating the difference, then fit to a common plane, and then everything results in a background modeling. Okay, so then again, once the background modeling is created, then again it will get splitted into background correction, adding the images to get the final mosaic, then register the mosaic. So all that these things. Okay, this is what we call workflow. Then we have several workflow technologies. That means how this workflow can be achieved using few technologies. So in that we have several. Out of that we have listed here four different technologies. So the first one is Kepler. So Kepler is a open source scientific workflow engine which is built from collaboration of several research projects. The system is actually based on Ptolemy second systems, which provides a solid platform for developing data flow oriented workflows. Actually, this Kepler provides a design environment based on concept of actors, which are reusable and independent blocks of computations such as web services, database calls, etc. The connection between actors is made with ports. Actor is nothing but it's again a node consumes data from input port and writes the data or results to the output port. Okay. Kepler is having the ability of separating the flow of data among the components from the, the coordination logic which is used to execute the workflow. So like that we have Dagman directed acrylic graph manager, that is Dagman. It is a part of again a Condor which we have already discussed in our previous section. Uh, it's a part of the Condor and constitutes the extension to the Condor scheduler to handle the job interdependencies. And this Dagman acts as a meta scheduler for Condor by submitting the jobs to scheduler in appropriate order. The input of this Dagman is a very simple text file which contains the information about the jobs and a pointer to their job submission files and dependencies among the jobs. Next we have Cloud Bus Workflow Management System, which is a middleware platform built for managing large application workflows on a distributed computing platforms such as Grid and clouds. It comprises of software tools that help end users to compose, schedule, execute, and monitor workflow applications through web-based portals. Uh, Next we have Offspring, which offers programming-based approach for developing workflows. Users can develop strategies and plug them into environment which will execute them by using specific distributed engine. The advantage of Offspring over the other platform is that ability of defining dynamic workflows. This strategy represents actually the structured or semi-structured workflow, which can change its behavior over runtime according to the execution of specific tasks. So in this next we'll see task programming model with Aneka. Actually, Aneka provides support for all task-based programming by means of task programming model. Actually, a task programming model provides platform for quickly developing distributed application using Aneka. It provides minimum set of APIs, that is application programming interface, that are very much needed, like task.it task interface. Uh, these interface along with the services supporting the execution of tasks in the Aneka middleware. So this is what the core feature of Aneka middleware. So actually here in this diagram you can see developers uh, can create a distributed application in terms of iTask instances whose collective execution describes an application. These tasks, along with the required dependencies like files and libraries, are grouped together and managed through Aneka application class. Here you can see Aneka application class comprising of task 1 and task 2, that is iTask 1, task 2. Okay, there may be a more number of tasks as well. Here Aneka application class is very specialized to support the execution of tasks. And then we have two components under this. That is, one is Aneka task and second one is a task manager. So Aneka task, actually it acts like a wrapper which is used by Aneka to represent the task within the middleware, while the task manager is the important component that interacts with Aneka and submits the task, monitor their execution, and collects the result. Okay, so in the middleware, in the middleware, four services coordinate their activities in order to execute the task-based applications. So maybe it may be a membership catalog that you can see in the diagram, membership catalog, task scheduler, execution service, and storage service. A membership catalog constitutes the main access point of the cloud and acts as a service directory used to locate the task scheduler service. Uh, and its main responsibility is to allocate the task instances to resources uh, and execution service for task execution and monitoring the task state. If the application requires a data transfer support in the form of data files, input or output files, an available storage service will be used as a facility for application. So the future that is provided by this task model are completed by web services that allows any client to submit the execution of tasks to Aneka platform. The procedure for submitting tasks through web service is as same as which you can do by using framework APIs, okay, application programming interfaces. The user creates the application on Aneka and submits the tasks within the context of this application. The web service limits the type of tasks and can be submitted. Only limited collection of tasks available for submission. in the Aneka platform. So that developing application, how can we develop the application with the task model? So using this task model, uh, which involves different components. Uh, Development is very much limited to the following operations like defining classes, implementing the iTask interface, creating a property configured Aneka application instance, creating iTask instance and wrapping them into Aneka task instance, and execute the application and wait for its completion. From design point of view, the process of defining task application ultimately reduces to definition of the classes that implement iTask, uh, okay, which will be those that contribute to form workload generated by the application.